Hey everyone, welcome to today's lecture, and it's going to be focused on embeddings and vector semantic search. And so, so today we'll kind of look at some introduction and motivation by looking at the example of recommender systems, right? And then using this as a motivation, we'll go into the idea of semantic search. And our mini project uh, one is focused on that, right? It's focused on embeddings, uh, semantic search, and also like Streamlit demo, etc. So today we'll also kind of have time to go through a Streamlit demo, a really basic version, but you can work on more intricate versions for your mini project. Okay. So I like to start with some motivation with Netflix recommendations, right? So Netflix is one of a classic use cases for recommender systems, right? And it's amazing the amount of algorithms and work that they put in to actually make recommendations, right? So these, for example, are my recommendations, and you can see there, and this is from some time back. So you can see there is like the ones that are popular on Netflix. There's the ones that are trending right now, and then there is also things that are personalized to um, to me, right? So things that I actually would love to watch is futuristic sci-fi kind of movies, and then it kind of has a separate row for it, right? Um, so yeah, so popular yet personalized is one, personalized trends is another, and then personalized genre is another, right? And there are other things that Netflix also personalizes. Any any thoughts on that from your observations? Like for instance, if you look at this movie, or I don't know if this is a movie or a series, right? This is probably a series. So if you look at this one, the image is also personalized. So that means the same series or the same movie will have a different thumbnail for you versus me, so that the propensity to click that series or image is higher. Like if someone is more into a rom-com or things like that, then they might see a thumbnail that's more appropriate for their style. Versus someone is more into action, for the same movie, you might see a different thumbnail that's more action oriented. So even the thumbnails are personalized. So your whole Netflix page, once you log into that account, is like hyper personalized, just so that you are able to go from one movie or TV show to the next. And I mean, this is like why a lot of people have kind of use the phrase Netflix and chill, right? And or they're like, I was just browsing a lot of Netflix because it is hyper personalized so that you can actually stay hooked. And yeah, so Netflix had $1 million prize um, sometime back. I think this is, as you can see, 2009. They had $1 million prize on what algorithms would actually help uh, that that can improve um, the accuracy of movie recommendations. So I think at the initial Netflix $1 million prize, every movie was rated from 1 through 5, right? Where 5 is really good, and then 1 is like really bad, and then 2, 3, 4 is something in between. So every movie gets rated, but you don't get to see all the movies, and don't get to see all the ratings. But the goal is to see if you can predict the missing ratings, assuming you have some information on certain movies and certain users, right? And so those who could, the team that could actually make the best prediction on unseen data set, they would get the $1 million prize, right? And so this was one of the teams, Bell Course, Pragmatic Chaos. They won that. And they also had a leaderboard associated with it. So, we also have something on a very small scale. So our Kaggle contest is going to be a leaderboard. So you'll see different teams that are forming in this course. You guys can also like pitch against each other and be part of a leaderboard, right? So, and in this leaderboard, you see things like best score. Um, so the best score, I believe it was based on, uh, yeah, I think it was based on root mean square error. So, so the RMSE is like, so it's the square root of the mean square error. So you would say, this is my uh, rating for a movie. This is my predicted rating, and this is the true rating. And then you sum it up over all um, movies and users, actually. It's both users and movies. So it's RIU, yeah. So divide by the total number of movies and users, right? So total number of ratings. So you take this metric, and um, the smaller this is, the better. So since the ratings are between 1 and 5, if I predicted 1 and then the actual rating is 3, then the error is something like 2, right? And if I predicted 4 and the actual error is like 1, then the error is 3. If I predicted 5 and then the actual rating, this is true and this is predicted, then the error is 1, right? So now you average all of this across all the possible user movie pairs, right? Each user rates every movie in the test set, and then you get the root mean square error. Average is RMSE. So if you see an RMSE is, so if you look at the score, right, from top to bottom, the score is increasing. Do you see that? So as you go down the leaderboard, the score is increasing, which means the root mean square error is increasing. So the lower the error, the better the score. So this is actually an error. It's all that says best score. It's an error. So that's why you see it's kind of increasing. So an error of 0.86. So let's say RMSE equals 0.86. What does that mean? It means on an average, the true rating and predicted rating, the difference is at most 1, right? So that means if you predicted 4, it's very likely that the true rating is 3 or 5. If you predicted 2, the true rating would be 1 or 3. So you're very close, but you're not exactly there. But you're as close as 0.85. So on an average, you're like only 0.85 away from the true rating. And it could be this way or that way, positive or on the negative side, right? So the team that won the $1 million prize, they had a RMSE error of 0.86. Yeah. And this is a percentage improvement of 9.78 over what Netflix had at that point. So Netflix hosted the $1 million competition, and what did they get in return? They got a 10% improvement on the performance on recommendations. So they also got a win because now they can deploy the best algorithm that came out of this. And then also the teams also got a chance to take a crack at it. So it was a win-win situation, right? Okay. So so there are uh, two main class of algorithms that are used for making these predictions for different movies. One is called collaborative filtering and another is content-based filtering. So we'll kind of look at the background behind each of these. So collaborative filtering, assume there are like 5 users, right? And then assume there are like 5 movies, right? So that means you have like a matrix of 5 by 5, okay? And every element here is a rating. This is R22, this is R25. So that means R25 is what? R25 is a rating of movie phi by user 2, right? Is the notation clear? So then you can basically index every element of the matrix, and then you will know exactly what that means. It means it's a rating given by one user for the other movie, right? So let's say these are the users and these are the movies: Avatar, Arrival, When Harry Met Sally, Before Sunrise, and Minions. So they capture a few different genres, right? So assume that you already have ratings, right? So thumbs up. So in this case, we simplify the rating, right? Um, Simplify ratings. So the actual, when Netflix came up with the price, the ratings went from 1 to 5. But to simplify rating, you just say like or dislike. You can also say it's like 1 or 0. It's like the Y that we predicted, right? Y is 1 or 0. Does that ring a bell? Yesterday we were looking at it. So, so 1 could be I like, 0 could be I don't like. Okay. So obviously it's not as simple as it, but it simplifies things. So let's say, I mean, and it could also be something like, how do you actually see this? Well, when you watch a movie, you liked it, you just like it. Let's say you were able to give feedback like that. And if you didn't like it, it doesn't mean you don't like it, but you didn't like it enough to give a feedback. Maybe you can assume that, right? So these are called implicit uh, ratings, right? So there is like um, explicit feedback versus you have implicit feedback. So actually, implicit is even more subtle. Implicit could even mean like I watched a TV show for 30 minutes. So if I watched it for a sufficient amount of time, it means I was interested. So that means you like that TV show. Otherwise, maybe in 5 minutes, I would stop watching that TV show or a movie. So that's an example of implicit feedback. Explicit is like you actually say, I like, I dislike, and things like, or I give a rating between 1 and 5. Okay. So feedback can be implicit or explicit. So however, let's assume that there is some kind of feedback, explicit or implicit feedback. Um, Implicit, explicit. Okay. So now what we see is that there are already some likes and there are some dislikes, right? So the question is, if you know some of the likes and some of the dislikes, can you predict what's missing, right? Um, can you actually predict this, and so on, right? So can you predict the missing ratings if you know some of the existing ratings? So what would be some intuition here, right? So let's say, let's look at this. So let's look at who are the users who are kind of similar. So if you look at Rishi and Karthik, right? So you see that both of them like Avatar. Both of them dislike this movie when Harry met Sally, and both of them like Minions. Okay, so there is a similarity. This is user-based similarity. So you can say Rishi and Karthik can probably collaborate in predicting the missing rating. So that's why the idea of collaborative filtering is there is some collaboration between users or collaboration between movies. So in this case, you can say there's some collaboration here between Rishi and Karthik. So here you would say, well, since these two are similar and Rishi has rated Arrival, maybe I should say for Karthik it's a like for Arrival because based on user similarity. I kind of identified this, and then similarly here I might say I kind of dislike this because there's a dislike coming from here, right? And there's a like coming from here. Okay, so that's a very simple example of collaboration. So this is a two-user collaboration, but obviously I could be, I there may not be any other user that's just like me, but I might be an average of 5 other users. So then you can extend this idea to collaborate with more than one user. So that's like you get feedback from many other users who are similar to me, and then I average and make a prediction, right? So that's another extension of this idea. Okay, so yeah, so then we have a like here, and then we have a dislike. Um, Here we spoke about that. And similarly, I can look at other users that are similar. For instance, Michael and Roshan are similar because there is a similarity in this movie, and then there is a similarity on Before Sunrise as well. So maybe if Michael likes Minions, I would say Roshan also likes Minions. And since Roshan dislikes um, Arrival, maybe we can say Michael also dislikes Arrival. Okay. So just completing this matrix, right? And so you can complete it and then you'll get, you can do the same way. And then now you get a completed matrix. So all these ones were filled out, right? This one, this one, this one, this one. They were all missing ratings, but they got filled out. So we filled in the missing ratings based on collaborative filtering. So essentially, collaborative filtering is using user behavior. You can also say user psychology to inform predictions. Okay. Right. Um, any questions on the setup so far with collaborative filtering?
I just wanted to comment that at the beginning, when you don't have enough data for new users or new behaviors on certain type of users or new movies, then you cannot have a good results with this, right? At the very starting.
Yeah. Yeah. So that's called a cold start problem. We'll get to that. That's one of the things we'll discuss as well. If you have a new user or a new movie, that's a cold start because there's no information available. So how do we handle that, right? That's a good question. So we'll get to that. Okay. So one of the ways, so we kind of gave an intuitive explanation for collaborative filtering as matching users together or matching movies together to figure out the missing ratings. But we also said that's too simplistic because there may not be a user that looks just like me. Like if there is a copy of me, I can just copy whatever they watched. Like, this is sometimes we do this, right? We ask our friends, did you like that movie? Did you really like it? You recommend it? Okay, I'll watch it because you said you like it and we are similar. I think I'll go watch it, right? So we are already doing informal collaborative filtering in our personal circle, right? but uh, but it's not realistic on like when you actually want to build a recommender system. It's not realistic to do something very simplistic like that. So you might want to look at more algorithmic ways to do these recommendations, right? And so one of the algorithmic way is a model called matrix completion that depends on matrix factorization. So the idea is that if you have a matrix with missing ratings, all these question marks here, if you can factor this matrix into a user's factors and a movie factors, then maybe you can predict the missing rating by taking the corresponding row and then the corresponding column, and then when you take a dot product, you get a rating, right? So somehow you can explain the ratings by seeing that for this user in this movie, there is a user factor which captures what the users might like based on their previous ratings, and then there's a movie factor that captures what the movie is about, what's the genre, what are the actors in the movie. There's some details there, um, and then when you take a dot product, you can make a prediction, right? So for instance, if you have this user Amy, and we want to predict what the rating is for a particular movie, then this is the user factor for Amy, right? And similarly, if you have a movie Arrival, and you want to predict the rating of Amy for the movie Arrival, you would have the um, movie factor here. So note that these factors are actually what are called latent representations. Um, Latent is also, another synonym for hidden. Um, it's also like, let me just think about this. Yeah, it's also connected to, the hidden layers and activations in our neural network. Because at some level, when you make the prediction, if you look at the neural network we looked at yesterday, right? So let's say we have inputs, and then we have uh, hidden layer 1, hidden layer 2, and then let's say there's one more, hidden layer 3, and then we have the outputs. So let's say that is like, let's say it's, you know um, predicting 0 or 1, right? So there's like, so you have this y. So if I want to predict, if it's 0, I would actually take uh, these activations, hidden activations, and dot it with the weights, right? So I have my activations here, A, and then I have my weights, W. So then I dot A dot W, and then I get my Y hat. So the dot product is a very important way to make predictions in deep learning. And so this idea that we're seeing here in a very simplistic way is what we see in this factorization as well. Once you factor and you want to say, does Amy like Arrival? Well, just take the dot product of Amy's representation, latent representation, and take with the dot product with the vector for the latent representation of Arrival, and then you will know if Amy likes Arrival or not, right? But these, and you can also think of these as weight matrices. So this is UW, and this is UM. What is UW and UM? Oh, sorry, I think I got it wrong. Let's do it. So I would say maybe it's like WU and WM. So what is WM?
User weights and movie weights.
That's right, user weights and movie weights. So we're just in the weight space, right? So remember here, if you look at this scenario, we're making a prediction for Y by taking the hidden activations in the last layer with the weights of between the last layer and the output layer, right? So if I want to make a prediction here, I take a dot product between A and W. But these A's come from X, right? So but here what we do is we actually learn a full weights matrix for users and weights matrix for movies. And all of this is learned, like this is going through some machine learning algorithm, just like we looked at yesterday. And then you learn the weights from scratch. And then you take the dot products as you get a query. Like, does this person like this movie? Well, then just pick the weights that you learned. So uh, WU and WM, the weights are learned from data through training. So these are not just any weights that you assign randomly. These are learned through a training algorithm, and they're learned to make sure that, on an average, a user's prediction for a movie is close to the truth. Like yesterday, we saw the loss function. Same way, there would be a loss function that can help learn these weights so that on the data that you can see, you do well. And hopefully on the data that you don't see, which is like the evaluation data, or like in the Netflix $1 million prize, everyone would get a certain set of data to train on, but they would not get to see what they would be evaluated on. So that's called the test data. So the train data is something that uh, the people who participate in the Netflix competition could train their weights on, right? But hopefully those weights are good for the test data as well, because you don't know what the ratings are. You can just make predictions, right? And based on the predictions, Netflix would come back and say, well, your uh, RMSE is 0.85. So this was given back by Netflix. You would just make the predictions. Netflix would have their ground truth, and then they would say, oh, on the hidden data, you're doing, we did the RMSE computation, and here's your score. So you just make the predictions, and then they have the truth. So they'll make the comparison, and they'll get back to you with your score, right? So that's how it works in the real world. Because if you know everything, if you know the truth, then why are you making predictions, right? So uh, going back, okay, all right. So the user weights matrix and the movie weights matrix are learned from data. So data looks like this, right? How does the data look like? So you could say the data looks like this. User 1, movie 10, it's a like, okay? Um, User 200, movie 1000, it's a dislike. So it looked like this. Now just given, and then you might have like, thousands of such data. So let's say it's called train data. So just based on this combination, okay, user X, movie Y, like, user X, movie Y, dislike. You just have this data from this data, you learn WU and WM, right? And then you learn to do well on train data, but hopefully you do well on the test data as well. Okay. Any questions on this? Okay. All right. So like we said, if I want to know if Amy likes the movie Arrival, I take the dot product here, right? And then when I take the dot product, um, actually it's not just dot product. Let's say it's because we need a number between 0 and 1, right? So we look at that. Okay. So we'll actually probably do some kind of cosine similarity, which gives a score between -1 and 1. So we'll take a look at that. So let's say it's zero point 0.9. That's a very good, that's saying that the prediction is saying that uh, Amy is very much likely to like the movie Arrival. So recommend the movie Arrival. So Netflix, what would do? It'd say, I'll show you Arrival. It'll be on the top of your carousel. So you log into Netflix, and then Amy will see Arrival waiting for her to watch it, right? So that's how the carousels would keep changing on Netflix based on these recommendation algorithms, right? So this is basically, this dot product is just linear algebra in action, right? And you might wonder, like, this is something you might have seen before. What kind of factorization does it uh, remind you of? If you've done some linear algebra in the past, this kind of a factorization you might have seen in some place.
Singular value decomposition.
Singular value decomposition, yep. So SVD is something that might be close to this, but SVD has three factors. So any matrix M can be decomposed into three factors: U, sigma, V transpose, right? So and we say that X is equal to U sigma V transpose. So X is the data matrix. So it's very beautiful. Like if you have any data set that can be represented as a matrix, and most data sets can be represented as a matrix, then to understand the data, there is a natural decomposition called the SVD, singular value decomposition, that can get you something like the users factors, then a movie factors. I mean, these things change. If you're dealing with something else, like if you want to understand if a user would like to purchase a home, then you'll have a user's homes matrix, and then like Zillow or Redfin would like to understand, Like, is this a home I would like to recommend to this user because there are some features the users might like, and then they want to sort their recommendation. Then Zillow or Redfin would have some, maybe instead of users and movie, they'll have users and homes, and then you have a user factor and a home factor, like to understand the homes, right? And then you'll pair up the user and the home, right? But this SVD also comes with sigma, which is singular values. um so it's a little bit different. Uh, but suffice to say that if you can combine the sigma into the U and the V, then you get back what we looked at earlier, right? So yeah, yeah. So as we said, yeah. So here maybe you combine U and sigma. You can also combine sigma and V transpose, whichever way. So then you get two factors instead of three, and then it's interpretable. In the previous case, the sigma, we didn't know how to interpret it. Like, what is the sigma doing? Maybe it's giving importance to the factors because it's a diagonal matrix. So maybe these values are telling you which factors are more important. But when you compress it to two matrices, now it's interpretable. Now I can say, oh, this is user factors, okay, and these are movie factors. So I can interpret it better. So you can say collaborative filtering methods, which is using user behavior and understanding how users prefer, like looking at behavioral data. This user liked this movie. I don't know why, but I think I have to figure out, reverse engineer why they like this movie. Or why did they dislike this TV show? I have to reverse engineer why they disliked it. So that whole process is collaborative filtering. Uh, the methods to do that, right? Um, so there is a catch with collaborative filtering, and this is something someone brought up earlier is, let's say there is a new movie that got released, maybe Men in Black 2 or 3, one is already released long time back. But let's say we had one of these movies, right? Men in Black 2, 3, and then it's an action, it's a sci-fi movie. And I have no idea because it's new, I have no idea what the ratings will be for any of the users. Let's say it's a new movie, it just got released today. I have no idea. So this is what we call the cold start problem. It's cold start because the movie is new. Therefore, it's a cold start. Because it's a cold start, there's nothing to support it. It would be a warm start if there was some data to support. But it's cold start, I'm starting cold. I'm starting with, it's like cold calling, right? I have no idea. Yeah, question?
Yeah. I guess I could see how it's a cold start on based on people liking similar things, but it may not be a cold start with respect to, other things like people looking forward to two unlikely actors working together or
Yeah,
um, a plot that's not typical or it's not necessarily cold in that sense. That may not be considered in this, but in terms of the out there in the world sort of sense, it's not necessarily.
that's right. That's right. So this is cold start from a behavioral user behavior standpoint.
I mean, yeah, as it's represented in there, right? But not necessarily as
Yeah.
that's what's possible out there in the world.
Right. It's cold start from the fact that we don't have any ratings data yet on it. There's no
Sure.
ratings on it.
Yeah.
Like you might predict ratings, that's different, but we don't have real ratings. Like, someone says, oh, this movie is going to be a box office blockbuster, but it bombed the next day, right? But that's not, we don't want to, we don't want to assume ratings because you might assume it's a blockbuster or whatever, or you would like it, but people may not like it for whatever reason. So we are saying it's a cold start from grounding in real ratings and real behavior that we actually observe, right? Uh, so real user behavior. Okay. But you're right. So that's what this is leading to is there's other information about this movie, Men in Black, that we could possibly leverage to say that you might be interested because there's similar genre, similar actors that you have seen in the past and you like these actors. I can infer that based on your movie history. Your movie history tells me like, oh, if there is this particular actor, you're almost always going to watch it. That's what we are kind of figured out. So then that might be also a useful signal. So that's where the next idea of recommender systems comes in is content-based filtering, which is to use content about the movie and understand the movie in a specific content-based way, and then you can use that to make predictions, right? So for instance, if I watch the movie Arrival and I know this is sci-fi, right? Then I'm also probably going to like this movie too because it's also sci-fi. And not just sci-fi, this is sci-fi with aliens in it, and then there's also sci-fi with aliens in it. So like very specific qualifications that you can add. So I'm probably likely to watch this from that standpoint. So this is not accounting user behavior, but it's if you had no other way to predict ratings, I might as well use the genres and the actors like you mentioned, like someone mentioned earlier, right? So that's the idea with cold start, sorry, content-based filtering is understand the content and encode it through an embedding, right? Embedding would be a representation. Again, if you look at the user factors, right, which we saw earlier, that's a embedding in some dimensions, like 50 dimensions, 100 dimensions. So here we see embeddings of movies in 2 dimensions, right? It's very unlikely that we'll use 2-dimensional representations to encode movies, but this is just for illustration purposes, right? So if you see the way the embeddings are here, let's give it some numbers actually, so we can actually understand. So this might be like, I don't know, minus uh, 0.5 comma 5 or something, and then this might be 3 comma 4. This might be 4 comma 3, and this might be um, I don't know, 7 comma negative 0.5. Okay, so the embeddings are in this case, so the embeddings in this example are 2-dimensional, right? So from this figure, we'd say the embedding of Men in Black equals 3, 4. Okay, so 3, 4 is our current representation or understanding of where the Men in Black fall. So 3, 3, 4 in and of itself may not actually convey a lot of meaning. But if you look at the relationship here, you can see that do you see a pattern to how these movies are getting stacked in this figure? Can anyone share what you're observing? So for instance, like you see that comedy is probably falling in this region, right? And then you can see that sci-fi is falling in this region. And then probably rom-com and other genres are falling in this region. So somehow, if you were to add more movies, perhaps they will start to stack in that way with these embeddings, right? Then it makes sense. So 3, 4, the number 3, 4 in and of itself might not make any sense, but 3, 4 and 4, 5, 4, 3 are close to each other as a vector, right? And you can see in the graph as well that they're close to each other. And so it makes sense, like, things that are close to each other might have a similar genre or similar set of actors or similar whatever content. And things that are far away have a different content. So that's the understanding here, right? So, of course, as we said, 2 dimensions is too small to capture an understanding of a movie or an actor, right? There's so many things about a movie. It's not just 2 things. There's the whole cast, there's the geography, there's the language. There's so many things that how can you compress it in 2 dimensions? So, but this is just for illustration because we cannot really visualize 3 or 4 or 5 dimensions, right? Maybe we can visualize 3, but not more than that. So embeddings typically are in 128 or 256 dimensions. So even for our mini project one, you'll see the GLOW embeddings that you'll get to work with, and these are for words, right? You'll see they're in like 50 dimensions or 100 dimensions and so on. So people have found universally in machine learning that about 100, 128 dimensions is sufficient for representing any object of interest. It could be a movie, it could be words, it could be images, it could be anything that you're working with as a data set. It could be real estate as well. Home, I want to represent a home. Okay, 100 dimensions, good enough, more than good enough. But those dimensions are latent. So you don't necessarily know what how to interpret any of those specific dimensions, right? But you can probably take a guess based on once you get the latent representation, you can probably tweak around and figure out, oh, why is this 0.5? I think it's 0.5 because it's capturing actors or it's capturing the specific thing. Is this actor present or not? Then this lights up and it becomes 0.5. If this actor is not present, it's like 0 or negative. So you might make inferences once you get the latent representation, but ahead of time, you don't know what these latent dimensions mean. So how do we obtain these embeddings? Well, we already discussed. One is um, you can get it from a deep learning model. Um, we cannot get it through collaborative filtering because we don't have behavioral data. We are doing content-based filtering in the scenario where we don't have behavioral data, but you can get these through a deep learning model. For instance, if you pass in a movie and then you want a movie and a user, and then you kind of want to, you have a network that takes in movie representation, user representation, and then makes a prediction if the user likes a movie, and that's a deep learning model. Then the last but one layer can help you get embeddings for the movie or the user, right? So one way to get these embeddings is from a deep learning model. For instance, you can take any LLM and then you can get an embedding for a sentence. You can get it for a movie as well, because you can just any sentence. So movie is also a word or a sentence, so you can also get an embedding for a movie. Yeah. And in the context of movie, like we said, the interpretation of what the latent dimensions are, it happens after the fact. So you could look at the latent dimensions once you learn the embedding and say, okay, it's comedy plus romance, or it's thriller plus adventure, it's comedy plus thriller, and so on. So there could be a mixture of genres and other things in here. Okay. All right. We also spoke about the idea that if Men in Black and Arrival are similar movies, their embeddings should be similar. Is there a metric that can capture that? Yes, the metric is cosine similarity. So higher the cosine similarity, the more close the two movies are to each other. And cosine similarity in this case is just the cosine of the angle between the vectors, right? So the closer the vectors are, the higher the cosine similarity. And the farther away the vectors are, the lower the cosine similarity. So you would say cosine similarity is a metric to understand if, on an embeddings-based approach, if two objects are similar, two movies are similar, uh, two words are similar, two sentences are similar, any two objects that you care about, right? Uh, so if these two have low cosine or high cosine similarity, you can also argue that these two have low cosine similarity, right? So Men in Black and When Harry Met Sally, for instance, they're orthogonal movies. I mean, would you say these two are related to each other in any way? Not really. Like one is pure sci-fi and aliens and everything, and this other one is more heart and rom-com and things like that. So it makes sense to separate these, and this graph is able to separate it out. And it's also separating Minions, like it's also separating this movie from Men in Black, right? It's saying, oh, you're comedy and you're sci-fi and you're rom-com, and so it's able to separate things. So the key takeaway here is that smaller the angle, higher the cosine similarity, right? So cosine of is high if the angle is low, right? So that makes sense. And how do we mathematically represent cosine similarity? Cosine similarity of two vectors x and y is just x transpose y divided by the Euclidean norm of x and Euclidean norm of y. So for instance, we said if the embedding of Men in Black is was it 3, 4, something like that, and the embedding of Arrival is 4, 3, right? So suppose I had to compute cosine similarity for between Men in Black and Arrival. What would I do? I would take the dot product between these two, 3, 4 dot 4, 3, and divide it by the norm of this, each of these, right? So what do we get here? So what's the dot product of these two? What's the numerator? So this is the time to refresh your linear algebra. So this should be straightforward, right? What's the answer? We really need to do a conceptual assignment so that we can all refresh our math on this. So yeah, it's 24 because it's 3 times 4 plus 4 times 3, right? That's 24. And then let's take the, this is the Euclidean norm. So that's a square root of the sum of squares of the elements in the vector. So what is this? 24 divided by 5 times 5. So what is this number? 0.9 something, right? So pretty high cosine similarity because the highest a cosine similarity can be is 1. So 3, 4, and 4, 3 makes sense for Men in Black and Arrival because they're similar movies, and the cosine similarity is also giving us a high value for it, which is 0.9, which is also telling us that the embedding representation for these two movies is correct. Like if you want to tell, I have all these embeddings, do they make sense? Well, compute these cosine similarities for similar movies and compute them for dissimilar movies and check that they are high for similar movies and low for dissimilar movies. Then you'll know that these embedding representations make sense, right? Okay, cool. So we did a quick cosine similarity computation for these two movies. Okay. And one of the facts about cosine similarity is this quantity is always between -1 and 1. So it can also be negative. Um, so here's a quick question for you guys. Will the cosine similarity between Minions and uh, When Harry Met Sally is positive or negative based on this graph? You can just put it in your answer in the chat. Is the cosine similarity between Minions and the movie When Harry Met Sally positive or negative? So you should think about this intuitively. Uh, do you think Minions and When Harry Met Sally are in the same genre by any chance? No, right? So that means uh, since similarity is the measure here, they should be dissimilar, right? So that means the cosine similarity should be small intuitively. So that also already tells you that it should be on the lower side rather than the higher side. So negative is lower, positive is higher, right? But also the math of it should also help you understand, right? So let's get some basics covered. What is cosine of 0? Cosine of 0. Don't ask ChatGPT on this. You should have, cosine of 0 is 1, right? That means the two movies are exactly aligned in the same direction. Okay, so then the angle is 0. Does that make sense? So even though the angle is 0, the cosine similarity is 1. So you don't have to look at the angle. Small angle is, that's why we say small angle is high cosine similarity. Because 0 has the highest cosine similarity of 1. Two things are very much aligned. They're similar, right? That's what it means. If you're aligned, you're similar. The angle is also 0 there, but the cosine similarity is 1. That's the highest you can have. Okay, what is cosine of 90? Cosine of 90 is 0, right? So, and that happens mathematically when the vectors look like this. They're orthogonal. The angle is 0. So you're going in one direction, the other is going in some other direction. They're not related. So the angle is 90, but the similarity is 0. So you see with Minions and when Harry met Sally, it's the second scenario, right? They're kind of going away from each other, right? There's no alignment. On the other hand, if you look at what is cosine of 180? So it's 180-degree angle. It's -1, right? So this is when your poles apart. You're pointing in one direction and I'm pointing the exact other direction, right? I'm not like we're poles apart. So that's why the cosine similarity is -1 because you're the most dissimilar you can be with -1. You're the most similar you can be with +1. Like look at the first scenario, look at the second scenario, and look at the third scenario. Yeah. If you look at these green and yellow vectors, you'll see in the first case, I'm the most aligned. The second case, I'm orthogonal. Like I mean, you're different genre. Like it's apples and oranges. The second one is like apples and oranges. The third one is like we're actually opposites, not even apples and oranges. We're like, you know, we're opposites in some sense. So um,
And
hmm,
so that means that your previous question was why positive and then is positive because are pointing in the same direction. Because if negative are like this, then when
yes,
you have a positive value, both are pointing to the same direction.
that's right. And the way to measure it mathematically is cosine similarity because the cosine of an angle is high if the angle is same direction. So that is 0. So that's why the yellow here has high cosine similarity because the angle is small. The red one here has lower cosine similarity because the angle is higher. Okay. Does this make sense? So the idea is if someone handed you the embeddings and you wanted to test, do these embeddings make any sense? Then you just want to do some basic cosine similarity calculations and see that when the cosine similarity is high, that is +1, the objects like the movies or whatever you're comparing actually are similar. If they are dissimilar and your cosine similarity is 1, then there is something wrong with the embeddings. But if your embeddings that you calculated are actually right, then when you take the cosine similarity, they will be high for similar objects and they'll be low for dissimilar objects. Okay, very cool. Um, yeah, there's a name for this inequality. It's called the Cauchy-Schwarz inequality that says that cosine similarity is always between -1 and 1. So this is most dissimilar posits, and this is most similar. And then we also have 0, which is orthogonal, like this is apples and oranges. Okay. Um, let's take a quick break. Maybe let's take a 7 or 8 minute break and we'll be back 5:10 and we can continue with this. Okay, so we covered cosine similarity as a very important metric. Um, to use embeddings to find similar movies or objects. And this idea of finding or searching for similar movies and objects is what we also call semantic search. Search for similar objects based on semantics or content. So embeddings motivate semantic search because once you have an embedding, you can do cosine similarity and find things that are similar to the referenced object. And then that captures the semantics of those objects, right? The embeddings capture the semantics or content of the object. And then you can do a semantic search.
Professor,
Yeah.
you explained the previous slide again, please?
This one or the one before?
Yes, that one about the semantic search.
Yeah, semantic search is, like here's an example of semantic search. Now, suppose there's a word, reference word. Let's say the reference word is mountain. And then I give you some candidate words. So let's say candidate words is valley, bike, road, class. So now given the reference word, which candidate word would you say is closest to the reference word?
What is the last one? Is valley, bike, road, and the last one?
Last one is class. You can just like call it out. What would be the closest to mountain?
Valley.
Valley, right? So this is semantic understanding. Is I may not have any other guidebook or rule book to tell me how to say this word is similar to this, but the embedding of the mountain and the embedding of the valley, they kind of are close in cosine similarity. So I'd say, oh, okay, I found the cosine similarity of valley is closest to mountain based on the embedding. And so the embedding captures the semantics of these words. And because the semantic is captured, I'd say, oh, close to mountain should be valley. Yeah. And then maybe the next closest might be road, perhaps, because sometimes roads go through mountains, might come up, but yeah, valley definitely is the closest, right? So this is semantic search. Is given a reference word, a reference sentence, what's the most appropriate candidate that's closest to it? Okay. Could also be with movies, right? Given a reference movie, so I can also have a reference movie, which is Arrival. And then I have candidates, Men in Black. I might have Minions, and so on. And then I'd say, oh, it's closest to Men in Black. Again, I understand the semantics of the movie Arrival. I understand the semantics of Men in Black. And I do that through this embedding. And then I take a cosine similarity and I say, okay, Arrival is close to Men in Black. Okay. Um, let's see if there's any other concepts. Yeah. So the other thing with embeddings is that you can embed different objects in the same space. Like here we are embedding movies, right? There's a movie, there's a movie. But you can also embed a user as well. So now that you've embedded user and movie, you can, so the idea is can embed both movies and users in a shared space. So then you can compare movie, you can compare movie user, you can also compare user. Make sense? So you can actually put different types of objects in the same space and then make comparisons. So not just the same kind of objects. So not just movies, you can also put, you can even put books in this space, you can put users in this space, and you can have shared space for embeddings if you have that kind of an application where you need to compare. And users and movies make sense because we motivated with collaborative filtering. We said, will this user watch a movie? So if you have embeddings for users, embeddings for movies, you can put it in the same space, then you can compare them as well. Okay. All right, let's move to, yeah. So like we said, movies is just one thing. You can replace movies with any random words. You can replace it with something else, right? And then this idea of embedding still works, right? So for instance, road and cars will be close to each other because they're semantically similar, but food is something a little bit more orthogonal to road and cars, right? And then flowers might be kind of close to road or cars because you see flowers along the way, but then flowers and food are kind of orthogonal, right? So you would want the embeddings for flowers and food to be different. So you can replace movies with other things like other objects like words, and then this kind of an embedding would still make sense. So in the mini project, you'll see that you use glove, and these glove embeddings are learned embeddings that have an embedding for every word in the English language dictionary. So let's say you have 200K words. Every single word in the English language dictionary would have an embedding through the glove embeddings library that you'll get to use in mini project one. And LLMs also, if you use LLM based embeddings, they can almost embed any sentence with any kind of words, regular words, kind of slang words. You can have any kind of words and you can get an embedding through these models, right? And then you can use it in a similar way for semantic search. Okay. You can even embed sentences. So although these are embeddings for words, right? These are words, right? But this is a sentence. You can also embed sentence in the same safe space. Here's a question for you. What's a way, suppose I have embeddings for words. What's a way to embed a sentence if I know the embeddings for the individual words? So let's say that the word embedding is, oh, so let's say that we have a word embedding that's like 128 dimensions, okay? So we have a embedding for food, for road, for cars, and for flowers. But I'm wondering how to embed this sentence. So how would you do that?
Can we concatenate them with some positional context?
Okay, suppose I
And
concatenate them. What would be the resulting dimension of this sentence in that embedding space?
that would explode because
That would
you have
explode,
like a
right?
lot of,
So
yes, because
I have
each
like,
word would be 128 dimensions.
correct. So if I concatenate, which is to put together these embeddings, right? One after the other, that's concatenation. So if I do that, I have like 5 words in this first sentence and I have 4 in the second sentence. So I would just have 9 times 128 dimensions. So then it would not fit in this shared embedding space. Any embedding in a shared embedding space should have the same dimensions, right? So although I want to embed the sentence, concatenation will give me an embedding, but not in this space, in some other space. So then it doesn't make it comparable. So what would be another way to leverage embeddings that we already have to construct an embedding for a sentence?
Perhaps
Uh,
we need to do the to divide in tokens.
Sorry, I didn't get that.
To divide a sentence in tokens and then explore the context, like using TDIF or bag of words or something to see the relation, the context between those words, but analyze it by using tokens instead of the complete sentence.
See, your goal is you can do whatever. The goal is to get to 128 dimensions. So my question is, what is the formula or what is the method you'll follow or you could follow given the embeddings for individual words to get to 128 dimensions for the sentence?
Do people ever use sum or average?
Average, yeah.
Average.
Average is a perfect way to do it. Yeah, that's a very good way to do it. Yeah. So how would you average? So let's say I love to drive cars. So in my word embedding space, each of these would be 128 dimensions. Do you agree?
Yes, we need like a weighted average.
Yeah. So one thing is you can just do simple average. So I love to drive cars. Okay. Each of these has a 128 dimension, let's say from glove. And then I can divide it by the number of words in the sentence. So here in this case, n is equal to 5. Will this give me a 128 dimensional vector? Yes, because I'm adding up 128 dimensions, that gives me 128 dimensions. I divide it by a constant number, by a scalar, and I get a 128 dimensional vector. So this will give me a 128 dimensional representation. So, okay, at least I'm able to embed it in the same space. Whether it's like the best way to embed sentence or not is a separate question, but at least I'm getting something in the shared space. Okay, so we have a start. Now, what could be a drawback of just doing an average?
You lose the positional context because now we don't know which word occurred when in the sentence.
Yeah, you lose the positional context. That's absolutely true. So why does positional context matter? Can you think of like, can you guys think of two words in English language, which if you order it one way, it means something, and if you order it the other way, it means something else? It has to be just two words, and it should mean two different things. It's like a two-word phrase, like lawnmower, okay? Lawnmower makes sense, mower lawn doesn't make sense, right? But are there two words where you can order it the other way and it also makes sense and has a different meaning? Okay, let me give you an example. I mean, think about example. If an example comes to you, you can share. I'll give you an example. So example of need for positional context. So this is example one. So milk, chocolate. What is the object here? Is it milk or chocolate?
Chocolate.
It's chocolate. Okay, let's reverse it. Chocolate, milk. What's the object here?
Milk.
It's milk. So if I average the embedding for milk and chocolate, and if I average the embedding for chocolate and milk, do I get the same embedding? Yes, because if you add two vectors this way or that way, it's the same vector, isn't it? So by averaging the embeddings of milk and chocolate or chocolate and milk, I get the exact same vector, but do they mean the same? No, one is a milk and one is a chocolate. They might be related because chocolate and milk come together in many ways, but they're not the same at all. So that is the reason why the ordering of the embeddings matter, right? And that's what we mean by positional context, is I need to know that milk came before chocolate, or chocolate came before milk, for me to understand what this embedding of a sentence should be, right? By just averaging the words, I might just capture the overall understanding. Okay, there's milk in this object and there is chocolate in this object, but I don't know if it's actually milk chocolate or chocolate milk. Does that make sense? So when you average words out in a sentence, you just get the average meaning, but you don't get the uh, positional information and precise understanding of whether it's a chocolate or a milk or however, right? So English sentence construction depends on the order to understand the semantics of a sentence. So averaging the embeddings is a start, but the drawback is it doesn't understand the positional context. So the summary is that average of word embeddings gives the same embedding for milk chocolate and chocolate milk. And like this is the drawback. Okay. But you at least have a start. And then you can also do TF-IDF based weighted average. I mean, any average, weighted average, you still have an issue with missing positional context. So we'll talk about how positions come into play for embeddings in a bit once we get to transformers. So that's where positional encoding will start to come. But you can start to see that word embedding is okay, but then once you get to sentence embeddings, you have to be a little bit more careful to capture the ordering. Okay. Right. Yeah. So we'll cover, glove embeddings is what you see in mini project one. You'll also see sentence transformer. And yeah, so there will be some positional encoding that is taken care in BERT. So when you do the averaging, you would still be in a better shape than just averaging of the glove embeddings, right? And yeah, so we'll look into some of the details of sentence BERT and things like that when we get to it. Okay, great. So one thing I want to say is that semantic search, like when you hear the word search, right? It's typically based on a trie data structure, and it's usually like tied to a search engine, right? When how does a typical search engine surface results? It's based on a trie data structure. It may not fully understand or capture semantics. It's based on rankings and things like that. So semantic search, on the other hand, helps us find the closest category for a given sentence, and it understands the semantics of the sentence or the query, right? Okay, let's look at all these things you've kind of covered. Okay, so with vector embeddings, you can do some things interesting. Like suppose I had this word king and I have an embedding for it, 128 dimensions. And then for man, I can also get 128 dimensions. And for woman, also I can get 128 dimensions. And then I'm saying this is vector arithmetic. So I would subtract these two vectors and I get another vector. So I get a resultant vector. And I can ask, what is this resultant vector closest to in the English language? So intuitively, when you look at this question, I mean, it doesn't make sense to add and subtract words in an arithmetic way. But suppose you did it in this way, what would be your answer? King minus man plus woman, what would be your answer?
Queen.
Queen. Does that make sense? It's just like saying, okay, should be like royalty, but not man, but woman. Okay, who's a royalty? That's a woman, that's a queen, right? So how would embeddings help with this? Is you would take the embedding for king, you would take the embedding for man, you take the embedding for woman, and apply this arithmetic, right? Negative, subtract here and then add here, and you get a result in vector, and then you search. You do a semantic search on this result. So if you do semantic search, you say, is it close to man? Is it close to king? Is it close to queen? Is it close to girl or something like that, right? And if your embeddings are right, then it'll say it's close to queen, and the cosine similarity will be the highest for queen, right? So this was like when this came out 15 years back, people were like, wow, you can actually do word math and you can actually get a result out of an algorithm. That's crazy. How can you subtract words and add words and make sense out of it? Like without vectors, there is no way you can make sense of this kind of a math, right? I mean, like you can talk about it, but how do you quantify it? How do you actually get an algorithm to do it? It is through vectorization. Because we have this vectorizability of embeddings for words, we are able to do this math. Okay. And I think I don't know if this is going to be I think this might be a question on your mini project, part one. I haven't taken a look, but okay. So that's about vector arithmetic. And let's take a look at a demo on semantic search. So let me just pause. Okay, so this is a demo, semantic search demo. It's really basic. I think it could be better, but maybe you guys can work on making it better. And it's based on Streamlit, but it's hosted locally, and you guys will get an opportunity to work on Streamlit demos like this, more sophisticated, more complete, but also you can host it on the web. So you can use Hugging Face hosting service to host your Streamlit app, right? So I think this doesn't mention the full context, but you can input any word or a sentence, and it has like a preset candidate words. We looked at those candidates in the slides. So it has some preset candidates it's going to search against for cosine similarity, and it's using glove embeddings in the background. So it's using glove embedding, sentence embedding, word embedding, everything. So you can type a sentence or a word, and it'll find the closest one to what you type, right? So let's try something like, let's try Jasmine as just a start. Um, so yeah, search uses glove embeddings, and the candidates are flower, mountain, tree, car, and a building, right? And it says the uh, closest candidate is flower. Makes sense. Okay, so this glove embedding is working. Does anyone want to give any word or a sentence? Maybe let's start with a word, some appropriate word.
Panda.
Panda. Okay, let's try panda. Um, wait, what happened? Did it actually say flower? Okay, let me try this again. For some reason it says panda is close to flower, although might say it's close to tree. That's interesting. So yeah, it's not perfect. We try Rainier, for instance, says it's close to mountain. So that makes sense. So Rainier is anything else? Any other input? You can even type a sentence like, I love going for hikes. Okay, so it says car. I thought it might say mountain, but maybe you have to drive to get to a trailhead. So car might fit in here. But you'll see that if you change the embeddings, underlying embeddings, and make the sentence embedding smarter, you'll get better results. So although you get some reasonable result here, you may not be satisfied with it. So this is something you can experiment with in the mini project, is to see are there better ways to do sentence embeddings that will give you meaningful results. Maybe I would say car is a second preference here and mountain is the first preference, but that's okay. Anything else? Any other sentences we want to try or words? You can just call it out. Um, building. How about White House? Because I see building here. Okay, great. White House is a building. Great. So we are on the right track. Let's see, real estate. Let me try for real estate. Okay, that's a building. That's good. So some things are straightforward and some things that are more tricky, I think it'll fail because you have to see that the glove embeddings are not foolproof. And also if it's a sentence, then we're doing the averaging. And let's try so tree and okay, let's try something
Like try chocolate milk and milk chocolate to see if they
okay,
give the
let's
same
try
thing.
that. But we don't have we don't have appropriate categories for this, right? So chocolate milk is a flower for some reason. Milk chocolate is also a flower. Yeah, that would make sense because we are averaging. So you'll get the same answer even if it's irrelevant, you get the same answer. I'm just thinking if there is something like milk chocolate between these five candidates.
Can you try beetle? Because beetle might get there's a car also, and it might get yeah, for flower as a category as well, because you might find beetles on flowers.
Beetle, right?
Yep.
Beetle is a
Oh,
tree.
okay.
Why is beetle a tree? Maybe beetles. Okay, yeah. I would assume it will be a flower, but is there a beetle tree? I don't know. Beetle nut? It's weird. But okay, it's something to do with nature. So I'm at least happy we got there. We didn't pick mountain or building or something like that. Okay. Yeah, so this is the thing, like embeddings, they all have different qualities and glove embeddings is just a start. You'll find in the mini project, you'll find a sentence transformer might give you even better results than what you're seeing right now. But that's the way, I mean, and these words are something that I chose. You can, for your mini project, you can play around with these candidates as well, right? It doesn't have to be this, it can be anything for candidates. And then you can do a search, semantic search, and then you can get a result. Okay. Any questions on this? Oh, let's try this. Treehouse, or what do you call it? Yeah, treehouse. It should be tree. Yeah, because there's obviously this. I mean, let me try plant house. Oh, plant house is a building. Greenhouse. Oh, greenhouse. Greenhouse is also a building. Why is it? Because it's a house. But okay. Okay, how about green room? Is green room? Green room is a tree. Okay, see, this is the issue, right? Is green room a tree or a building? It should be building, right? But if you average the words, probably room is coming in as the main category, and that's connected to a building. Sorry, probably green is coming in as the main one, and so that's connected to tree. So maybe that's why, these are the issues, right? With just averaging. So and not considering positional effects, you'll get weird results. So I think, yeah, we'll probably have a demo where, yeah, you'll be using sentence transform in mini projects. So you'll get to play with it and see if it's making more sense.
What happens if you put in large thing?
Sorry?
Large thing. Or
Large
just like,
thing.
yeah. I'm curious if it's mountain or okay, yeah, building.
Yeah. So it favors building than mountain. Okay, yeah, so overall it kind of makes sense, but it's like, again, like we discussed, there are the drawbacks of averaging embeddings is what we are seeing here. Like especially with the green room example is a very good one, that you're getting it to be a tree instead of a building. Okay, so I'll stop here for today and